let's continue our discussion on syntax directed translation. We said that SDD, syntax directed definition, is more at the abstract level, more in the pseudocode form, whereas SDT, syntax directed translation, is more about the implementation of that. And then we looked at two types of attributes. One is the inherited, another is the synthesized. Inherited goes from top to bottom as well as from the siblings plus those within that particular node. And then inherited attributes come from below as well as those which are interdependent in the same node. And we looked at the order in which these attributes and their associated assignments need to be evaluated. And we realized that in some cases you might be able to do away with only top-down evaluation or bottom-up evaluation. Whereas in some cases you might have to go top-down as well as bottom-up. And in general there could be circular dependencies across these assignment statements or across these attributes. In which case there exists no explicit evaluation order. And therefore we looked at only the S-attributed SDDs, which is only about the bottom-up traversal of the assignment statements. However, S-attributed was too restrictive, and therefore we wanted more evaluation orders to be allowed. And that led to that we could have S-attributed SDDs. In addition, we could allow some more use of inherited attributes. However, we disallow the cycles that get found, and that leads to an L-attributed SDD. And this was our example of expressions on digits using multiplication operator, which allows us a good evaluation order, or an evaluation order exists, which means that there are no cycles in the dependencies. And the example is shown here for 3 into 5. Okay, so there exists definitely examples of non-attributed SDD. I'm just giving you one small example. For example, if there is a production A deriving BC, and there is a synthesized attribute, which is, or there is some attribute which is dependent on some attribute of the head, which is dependent on some attribute of the non-terminal in the body, then that dependence gives rise to an S attribute, like a synthesized attribute. Similarly, there is an attribute of B which is in the body, which is dependent on the attribute of A, which is the head, and therefore this dependence leads to an inherited dependence. Sorry, not inherited, this is the synthesized one, because it is coming from, no, this is inherited, this is fine, this is inherited. So therefore we make use of these. Because of this dependence we have both the, on the same non-terminal attribute A.S, we have both ways dependence, and therefore this can create a cycle. So the first rule uses synthesized, the second rule uses inherited, and B's attribute is dependent on C's attribute, right, which is on the right. Yeah, so that is another one. B dot C to B, there is a dependence from C dot C, which is on the right hand side, and therefore we are, according to this, we have inherited attribute usage. So this is definitely not an L-attributed SDD, because there is dependence from the right hand side, because we said that for L-attributed we need it coming from above as well as coming from the left hand side non-terminals. So C can have a dependence from B or A, B can have dependence from A, right? But B having dependence from C is a problem, right? Similarly, A having dependence from B is a problem in the first one. Hence it is not an L-attributed SDD according to our definition of L-attribution. Okay. Any questions so far? Okay. So then let's do a classwork. So I am giving you a particular grammar, S deriving L dot L or L and so on. It's something to do with zeros and ones, that is binary numbers, but there is a dot in between, and what that indicates that you have some bit string of zeros and ones followed by a dot and then some other bit string of zeros and ones. So what we have to do is that, first tell me what this grammar does. Anyway, I think that is kind of clear that there is a bit string of zeros and ones followed by a dot and then another bit string of zeros and ones, right? And there is single dot in it. So it's a kind of floating point number using binary. Right? So we want to create an L attributed SDD, right? Which means that dependence from right to left as well as such things, for example, from C to B, etc., is not allowed. Okay, I think I made a mistake in mentioning that. A to B is okay, B to A is also okay. Okay, so this part is okay, this part is okay. This C part is the disallowed part. So we said that synthesized are okay. The inherited are also okay as long as those are restricted, and those restricted ones are the ones which is coming from A. Okay. So we have to design an L attributed SDD to compute the value of capital S, assuming that to be the starting symbol, which is the decimal value of the input string. Just to give you an example, if the input string is 101.101, right, it should output the value of the decimal value of this, which is 5, and the decimal value of the 101 string, which is coming at the right hand side of that, which should be 0.5 plus 0.125, and that is 0.625. So that is what we want to do. If you can do it without L attributed SDD, that is also okay. So please try that and let me know if you face floating point numbers, floating point. So so let's write that and let me know if you face any trouble. Sure. So this 101 is the binary representation of 101 is 5. That part is okay. This is 4 plus 1. This is about the numbers after the decimal digit. So this one is going to be 2 to the power minus 1, 2 to the power minus 2, and 2 to the power minus 3. And that will be 0.5, first one. And then this is 0.25 and this is 0.125 and so on. And then we add those 0.5 and 0.125 to get 0.625. Any other concerns here? So as you try attempting it, you will see some difficulty. Let me know if you encounter any. By the way, the string also allows, the grammar also allows strings without dots, which means that those are to be regular integers. So that part is relatively easy. In fact, if you want to go step by step, you could try only for this L first, ignoring L dot L, and just see if you are able to compute the value of S only for that L, and then you can get into the S dot val is L dot val plus dot size L1 dot val. Okay. So L dot val is L dot val into 2 plus V dot val. Okay. So what is the difficulty here? V dot val is dot val equal to L dot val. Sure. So as Venkat has suggested, we need to know whether that L that we are talking about is on the left hand side of dot or right hand side of dot, because the evaluation kind of differs based on that. Right? We have the same strings 101, but the evaluation of them turns out to be a little different. Right? So okay. So there are multiple ways in which this can be solved, and one of the ways is that as far as L is concerned, this part, you kind of evaluate it without worrying about whether it is on the right hand side or the left hand side. And based on when you reach here in S dot L, S deriving L dot L, at that time we are going to make use of whether it is on the left hand side or the right hand side, and then evaluate the value of L. So L dot val is going to get kind of computed for the left hand side of L. Whereas for the right hand side of L, we will have to do some juggling. So we are going to make use of the size of the attribute, size of the string which is going to appear. That is one way in which it can be done. For example, can we do the change SDD L dot L double prime? Yeah, that is another way. Yeah, so I was saying that, like Raghu was suggesting, we might have to keep track of the size, and that size might be useful for you to do 1 upon 2 to the power of that particular one. So 1 upon 2 to the power of size to come to this. Sarka's question is, can we change the grammar and then possibly replicate those L rules? Right? That is also one way in which it can be done, although that will require you to change the grammar. Right? So in general, we expect that the grammar should not be changed. But yeah, if you are actually implementing it as part of your work, then it's possible to change the grammar so that then there is distinction between the two L's, and then you will be able to really take care of having separate actions for both of them. Yeah, but if you have to retain the same L for this purpose, then yeah, so that was one way. There was another which I was mentioning. Can we have a top-down flowing attribute which tells which side of L belongs to? Right. So that was the second option which I was suggesting. That for this first L, we mentioned that it is the left hand side L, and for the second L we mentioned or try that it is during the top down part of the parsing that it is the right hand side L, and that attribute you can get in, so that is the inherited attribute which comes from the first root, and that tells us by the time you are in the third root, that is L deriving LB, that L dot side is left or right or 0 or 1, and based on that you apply a particular root, either multiply by 2 or divide by 2. Right? So that is another way in which this can be done. In which case you don't have to then worry about the length of the string. Right? So we see that there are multiple answers given based on these two aspects, and either of them should work out. In the first case, that when you are keeping track of the size, you can get it done without using that inherited attribute. Right? It is still an L attributed SDD, but more importantly, it is an S attributed SDD. Right? If you just keep use of the size, whereas if you keep track of the side, left side or right hand side, then it requires inherited attribute, which leads to L attributed SDD, and you will see that there is no cyclic dependence that gets created. Okay. Any questions on this? All right, let's move ahead. Yeah, so that is what I was mentioning. So there are a few simple applications of this SDD. I mean, SDD gets used in deciding the actions, but there are some specific applications which we show usually. I'm just going to show you 2 or 3 applications. So we can actually build an explicit syntax tree using an SDD. Explicit syntax tree is often very useful. In fact, in many compilers, the intermediate representation is one part, but as far as output of parsing is concerned, that can be given as an abstract syntax tree, on which you can decide to perform optimizations at the source code level. Right? IR will be more at the intermediate representation level, where it's going to be kind of far away from the syntax of the original program, whereas in just after parsing you still have almost the same syntax as the original program, and sometimes the transformations are useful to be done at that level. So if you require an explicit syntax tree, SDD can be very useful. For example, if you have an expression a minus 4 plus c, you might want to build the explicit syntax tree so that you are able to perform certain optimizations. Maybe you want to take advantage of algebraic things. For example, maybe you know that plus is commutative, and therefore you might want to reorder some things so that the cache efficiency increases. Right? So all of these are the number of loads reduces and so on. So these all applications are possible when you can reorder the syntax tree. For that you need some explicit representation of the syntax tree, or you can do it even in other ways, but that is one definite example of having an explicit syntax tree. Right? So for example, if I have our favorite grammar, like e plus t minus t, etc., I might be able to construct an explicit syntax tree by creating different nodes for, let's say, different operands and operators into this expression. Right? So similar to what we have here. So what I'm going to show you is some pseudo code type of statements which are going to help us build this tree. So let's look at that. So let's start from the bottom. So $$ is the left hand side. That is new leaf of $1, which is the number that I'm talking about, or new leaf of $1, which is the ID. And then t deriving e just adds $2, that is e's node to the left hand side node. E deriving t is also similar, whereas e minus t requires me to create a new operator, which is minus. Right? And then it has 2 children, $1.node which is coming from below, right, which is coming from here, ED-T, as well as $3.node, which is possibly coming from one of these things. Right? So, and that gets moved to $.node. So, as soon as you execute these actions, which means that as soon as you parse this given expression, by the end of the parsing, in E.node here, like the starting symbol .node, you will have the pointer to the root, and it is going to be pointing to the actual syntax tree. Yeah, so just in this case, these are the operations which are going to happen for this particular example. But I'm going to create a leaf for A, and I'm going to create a leaf for the number 4, and I'm going to create a minus thing, which is minus node, which is this. Then again I am going to create a leaf. So this shows that there is a left to right associated, left to right parsing that is going to happen. And then finally I am going to create an operator plus, which is going to get a return as the attribute of the head node, of the start node. Any questions on this one? Okay. Alright, so let's change the grammar, and I want to generate the syntax tree using that following grammar, similar to what we had for the previous one. As far as TIID, TRNM is concerned, that you can use as it was for the previous one. And syntax is not so important what function you are using, but maybe you can use $$ for the left hand side, or you can use T also, or T1. Yeah, in this case E1 is there, and so on, but yeah, you could use either of them. Yak-like syntax or pseudocode-like syntax. In fact, for T it should not be a problem, that should follow from what we had for the previous one. E prime is the new non-terminal. That will require us to think a little bit about how we are going to apply the operators. Any suggestions? So what should be the rule for E deriving T prime? Or maybe we will start bottom up. E prime deriving epsilon. What should be the rule? So similar to what we had, dot one equal to 0. Yes, because we have plus and minus, so the identity element is going to be 0. And there is something more. We want to build the syntax tree. Dot L equal to 0. Yes, but as I was mentioning, so last time when we did it for multiplication, similar to this. We were interested only in the value, so we were just assigning the value. But now we are interested in creating the tree, because there is probably the value may not be computable. Okay. So E prime dot val okay. Synthesized attribute is dot inherited. Very good. We need to know the operator as well. Okay. So one possibility is that, so the way you should think about it is that there is some part which is going to come in the end, right? And that is going to be epsilon. Please believe that this is epsilon. So that is going to happen in the end. So what do you want it to return? Right? So that is not adding anything to the syntax tree really, except that whatever you are doing from top to bottom, the reason being that you are going to require some sort of moving from E to T prime. Right? So there needs to be something which is going to come from E to T prime or T to E prime, and that is available to you as an inherited attribute, and that change has to happen so that you are going to go bottom up using something similar to what Harini has mentioned, that the synthesized attribute needs to be getting something from the inherited attribute. We need to know the operator as well. Well, that could be one way in which it can be done, that you can pass on the operator also from, for example, from here to here, as well as from here to here. That is one way. Alternatively, that even prime's attribute, the node corresponding to it, could just be present in this particular prime, apply this particular position plus T prime 1. At that time, you can use the operator as well as whatever is written from E1 prime to kind of combine the nodes. Okay. So that is another way in which this can be done. Okay. So let me show you that. Any questions on this so far? Any discussion before I show you the answer? Yeah, but the important part here is that this is an L attributed SDD, and therefore you need to have both top-down as not because of that, but you are using both synthesized and inherited attributes, and therefore that top-down pass needs to be followed by the bottom-up pass, and that E prime deriving epsilon is the right place where that switch happens. Okay, so let's look at that. So these three, for T were the same, so that is not a problem. This part is where the switch is happening. So you are going from inherited attribute to the synthesized attribute. What does the inherited attribute tell us? Well, inherited attribute is telling us this part, minus TE prime 1. which is going to tell us that take whatever was already computed using the $$ inherited dot and apply the minus sign there and t, right? So that is the previous part of this expression, which is going to be already there, computed. That is, the syntax tree is already computed in E prime. That E prime you take and $to that node, that is t's node. So E prime minus t, that is what we are essentially doing here. And once I have that we are going to pass on to the inherited attribute of E1 prime. Right? So that by the time you reach E1 prime, you have this information available and you can pump it any number of times, or that E1 prime might appear in the plus, right? So these two are similar. When you are going to do the bottom-up pass, at that time you just need to, whatever is computed for this E1 prime, this E1 prime synthesized attribute, that we need to pass back above, right, to E prime. So that is what happens, that $3 dot synthesize, which is E1 prime synthesized attribute, that needs to be passed on to $$ dot synthesize. So that is the bottom-up pass. The plus t prime is similar. Let's see what happens in this first production. In this case, as far as the synthesized part is concerned, that is what is the value that is going to get returned from E prime. Right. So that is what was coming from below. Right. So that part is okay. But initially, for the inherited part, $2 that inherited, which is the E prime, that should get the value of the syntax tree, which is rooted at t. Right. So that t's value gets passed to E prime, and from E prime it starts going below and below with evaluation with respect to plus t or minus t with respect to E prime. So that E prime plus t, E prime minus t happens, that gets passed to the next E prime and so on. So this goes on happening, and that makes sure that your associativity is retained. Right? So that is important here. There is no precedence because it's only plus and minus. There is parenthesis, of course, but that is not causing any trouble here. Okay, any questions here? This is quite similar to what we did with respect to the evaluation of the expression. It's just that in this case, I mean, the order is going to remain the same, just the action corresponding to it is going to differ. So although we are writing the actions in the same place, as far as our SDD is concerned, the YAP syntax is going to differ. YAP syntax will force us to write the inherited part in between. Right. So we'll have to write it somewhere in between. Before E prime gets evaluated here, between t and E prime, since we want to move $1's value that we have computed, that is t's value, to E prime, we will have to put that action in between. So the inherited part we will have to put in between. The synthesized part can come at the end of the action. Right. So therefore, automatically the order gets decided by left to right ruling. But the way we write it in the theoretical aspect, like on this slide, we write both of them together, and then depending upon whether it is inherited or synthesized attribute, their order gets different. Okay. Any further questions? Okay, so we'll move ahead. Another application of SDT is finding the type expressions. So type analysis is one of the very important aspects of compilation. A little bit of that gets covered in Principles of Programming Languages Elective, which Krishna offers. So there is a large theory behind type. So if you have the type information available for a variable, you'll be able to make large number of assumptions about what kind of operations you can have on those types, especially in the more like strongly typed languages such as C, C++, Java, etc. But if you have more scripting languages, there the types, again, as far as programmer is concerned, the programmer can make use of the same variable in different contexts. The same variable can be used as a string, as a number, as something else, etc. But as far as compiler is concerned, either the static compiler or the dynamic, that is the JIT compiler, in, for example, JavaScript. Right? So you can perform these optimizations, perform these transformations from string integer anytime, or in Python. But while executing the code, one needs to still know what is the type of that particular variable. Right? So this type analysis, either statically or dynamically, this requires to infer the type of that type of the different variables. So in case of static, in case of strongly typed languages, this type is already given at compile time. In case of dynamically or weakly typed languages, this type gets inferred at runtime. Even in case of statically typed languages, the type can be inferred. For example, your shell script, for example, or even Python for that matter, unless you have dynamic boundings associated with variables. So identifying this type information is useful. For example, if just to take a small example, if I have int a of 2, 3, it's an array of 2 arrays of 3 integers, right? So in functional style or in some style, for example, there might be representation in your symbol table which tells you what is the type of this array, and the types can get nested quite arbitrarily large. As you can see, there could be 4 levels of this array. Then part of that might be a structure. Within that, there might be an array type or a pointer type which might be pointing to some array and so on. So there could be a large combination of such types, and it can get involved as the program gets large and you use complicated data structures. Even in the context of STL, the way we use different types, although at the programmer level we don't worry too much about what is getting used, we just use vector of vectors, but internally it might be a little complicated than simple 2-level nesting. So in such cases, you might have a representation of these types in the symbol table, and that representation, one of the representations could be in functional style. For example, I can say that there is an array of 2 arrays of 3 integers, right? So that could be one way of representing it. And if I want to build such a tree corresponding to such a representation, such a functional style, I could mention it something like a syntax tree. There is an array of 2 arrays of 3 integers. The question is, can we build such a tree either in the syntax tree form or in the functional style form? So can you build the grammar, and then can you build the SDD corresponding? So your input is just this type, identifier, and then a sequence of rectangular parenthesized expressions. Maybe you can say that it is not expression, it is only an integer. That is also a constant rather. So can somebody tell the expression, the grammar? on the grammar? Type array size and type or basic type. Type ID br comma br. Okay, br comma. Okay, that's the next correction. Br derives br of constant or constant. Yeah. Okay. Alright. So we'll wait for a few more seconds in case somebody wants to try that out. Okay, so yeah, so here is my grammar. The BID, C where B is just that type or int or float, whatever, and then C is essentially, so this is similar to what Sarthak has written, except that I am using an epsilon production, whereas Sarthak is not using an epsilon production. Because I think I am allowing also the non-array declarations here. Okay, but that doesn't matter, that's okay. So, okay, so given this grammar, I want you to think about how to create such a representation, either this or the tree-like representation. So please write the SDD corresponding to this grammar. Again, the kind of functions that means is going to be arbitrary, so that is not a problem. But it should have the same semantics. C dot dimension equal to num into C dot dimension, that is 4, 1, 2, 3, 4. Num into C dot dimension. Okay, 0 dimension equal to 1. Okay, so this multiplication will probably make it as how many memory locations or how many elements exist in this particular multidimensional array. Right? So the number that we have, that is the num, and then C dot num, that multiplication will give us the total number of elements of this k-dimensional matrix. But that will not give us the individual values. So, yeah, there is a little bit of catch here, and the catch is to understand that this int is coming at the bottommost layer, right? So it is coming here. Whereas in the declaration, it is right on the left of the expression, which means that is somewhere at the top. During parsing, you are going to enter it initially. Whereas in the expression, we want it at the bottom. So such an expression is going to be very, such a grammar is nicely parsable using a top-down parser. But because we want this int to be here, a bottom-up parse is going to be more helpful, and that gives you some indication that you require both inherited as well as synthesized attribute. So that int needs to be passed down like this, and then that int needs to be used. The reason being also that that much. So that int needs to be pushed down, and then it needs to be brought up using the repeated application of C. There are no C dot dim equal to num, comma, C dot dim. Okay, so sure, that seems fine. 5 can be $.type equal to C dot inherited. $.type equal to C dot inherited. Yeah. So where type is the synthesized attribute, and that switch happens here. So that seems to be fine. That seems to be fine. They will move that int somehow, right? So essentially from B we are going to get that, right, as an inherited attribute of B, and that needs to be pushed onto C here. That C, that C dot type is going to be pushed from here to here, so that it goes on. However, num need not be pushed because that left to right, so it is the right to left associativity, right? So that 3, not associativity, I think associativity is the right term. So 3 needs to appear in the subtree, and then that needs to be combined with 2, right? So therefore it is right associative. So 3 needs to be evaluated first. So therefore that num should not be pushed to C1, right? So num should be used here itself, right? So for that you need to have C1 dot type computed, or that expression computed, which needs to be combined with num, so that becomes num followed by C1's type, and that needs to be added to left hand side C's type, so that it then goes up for the, that gets pumped into the same production multiple number of times. Okay, C dot inherited B dot node. Okay, C dot synthesized equal to new op of num array C1 dot synthesized, that is fine. And then C1 dot inherited, that is the rightmost one, that is C dot inherited, right? So that type needs to be pushed down. Except that, so the order of these two, so these two statements, C dot synthesized equal to and C1 dot inherited equal to, this order is kind of immaterial because we are going to identify the dependencies automatically, but we expect that C1 dot inherited happens first and then C dot synthesis. Okay, so that's fine. And then C dot synthesis becomes new node C dot inherited. That seems to be fine. So what Krishna has written is to create the syntax tree. What I am going to show is to create the functional expression. So let's look at that. So we have this, this happens in the end, t dot type equal to c dot type. But initially c dot I is b dot t, right? So that is what we were passing here, the inherited attribute. The b dot type is coming from here. The c dot type, that is the left hand side, is the bottom of part is the array using num and c1 type, right? And the c1's inherited part is going to go below, and that is going to be coming from c dot inherited. So whatever is int or float, that needs to be passed on, and this is where the switch happens between the synthesized and the inherited. The synthesized gives the inherited part. Any questions on this one? Okay, so we'll stop here. See you tomorrow.